Hello everyone! Man, it's been a while since I've recorded, but welcome back to Physics Friday. And today we're going to be going over and delving into a little bit at least Bose-Einstein condensates. This is basically the state at which essentially all particles occupy the lowest energy state possible, which gives it some unique properties. But today what I want to focus on in this video is really just the temperature at which this occurs. And to find that, we're going to start off with this nice little integral right here. I say little, it's quite big. This can just be found in Griffiths, where he derives it quite nicely, actually. But we won't be doing that here. I'm just going to be yoinking it for this video. But the number of particles, or this actually just follows from one of the constraints that you have when doing some statistics with gases. But what we have is our number of particles is equal to our volume divided by 2 pi squared times the integral from 0 to infinity of k squared over, and this is where there's a lot of numbers here, h bar squared k squared divided by 2 times the mass times Boltzmann's constant times t, and then minus 1. And we're integrating with respect to k, of course. And essentially what we want to do is evaluate this integral right here, and then solve for t, because what we've essentially done in this formula is assume that the chemical potential is 0, and as such, if we solve for t, we can find the critical temperature at which the Bose-Einstein condensate is formed. So, let's get cracking. You might be wondering, how on earth do we evaluate an integral like this? And my first step here is really just to, it's not even a u sub, it's just saying c is equal to this whole mess up here, I mean minus the k, of course. This whole h bar, Planck's reduced constant squared, over 2m kbt. That way, whenever we do our u sub, this makes our life so much easier. We can literally just say, well, u is equal to ck squared, meaning that du right here is equal to 2ck dk, which gives us that dk is equal to du over 2ck. So all I'm going to do is sub that in real fast, meaning that our n is equal to our v over 2 pi squared still, times our integral, our bounds aren't changing, but times our integral, and we have our k squared over k, so I'm just going to write that as k on top, simplify that now, over e to the u, that's just by definition, minus 1, and then times du over 2c. But we still have this k right here, and all we have to do to get rid of that is just solve for k right here, giving us, and if we solve for k, we find that k is just equal to the square root of u over c. Moving this 2c, actually I'll sub it in, then move everything out. So this just means that our n, again, is just equal to v over 2 pi squared times 1 over 2c times 1 over the square root of c times the integral from 0, oh goodness, that's a nice integral. Integral from 0 to infinity of u to the 1/2 over e to the u minus 1 du. And now our integral looks a lot nicer, but we could, use some analysis and, derive the formula, but I'm going to save that for a separate short, actually. And you'll just have to take my word that this right here is just going to be equal to gamma of 3/2 times zeta of 3/2. You'll just have to take my word for it. Again, I'll prove it in the short. Probably quite soon, actually. I might make that today. We'll see. But moving on from that, this just means that our whole expression right here, our n, is equal to v over, let me see, that's a 4 now, 4 pi squared times c to the 3/2. I'm not forgetting any terms. times gamma of 3 halves zeta of 3 halves. And one way to simplify this even further, actually, is to look at this and realize this is 1/2 factorial. And again, I'm not going to prove it in this video, but 1/2 factorial is just the square root of pi over 2. I've been doing math for too long. I should know that off the top of my head, but at the same time, I mean, it's a math channel. I feel like it's kind of a flex. But anyway, this just means that our n right here, subbing that in, is v times the square root of pi over 8 pi squared c to the 3 halves times zeta of 3 halves. It should be noted that zeta of 3 halves is just a transcendental number in and of itself. You can't really express that in terms of pi or e anything, to my knowledge at least. But yes, so what we have here then is an expression with n and c and pi's and zetas. But what we wanted to do originally was what? Solve for T, the critical temperature at which this occurred. And you'll notice that our temperature is actually hidden away in this C constant. So what I'm going to do is solve for C, and then, or solve for C in terms of everything else, and then, you know, oh, meant to underline, make that substitution, and then that will be our critical temperature. So what we have then, solving for C, is really just C is the 3 halves, is equal to our volume over 2 to the 3rd. There's a reason I'm writing it like that. Don't worry. Times pi to the 3 halves times zeta of 3 halves. Don't believe I'm forgetting any terms. No. Okay, that's like the worst thing with doing this. Or, I was forgetting a term, n. That's the worst thing with doing this, forgetting terms. But now, just raising this to the 2/3 power, we find that this right here is just v times zeta of 3 halves over n to the 2/3. And then we can just simplify this bit right here, where this 2 to the 3rd, or 2 cubed just becomes a 2 squared, meaning we have 4, and then pi. So, we're almost there, I swear. All we have to do now is substitute in C, where C was our h bar squared over 2 times our mass times Boltzmann's constant times our temperature. I think. Let me double check that. Yo, no way! I was right. Okay. I should really change color. I'll change color now. But this right here is just going to be, well, this right here, because that's C. So this right here is, well, I'm not going to write it out again. I'm just going to kind of solve for T. This means that T is going to be equal to h bar squared over 2mkb, and then just times 1 over all of that. So then what we have is we're multiplying by 4 pi, and then just, switch the numerator and denominator there, so that we get n over v times zeta of 3 halves to the 2/3 right here. And simplifying this just a tiny bit, we find that Tc, our critical temperature below which our Bose-Einstein condensate is formed, is equal to 2 pi times Planck's reduced constant squared over our mass of each boson times Boltzmann's constant, and then times n over v. This right here is actually just our particle density, times 1 over zeta of 3 halves, all to the 2/3 power. And that right there is, well, I would say simply, but I don't know, it doesn't look so simple. But at any rate, that is our answer right there. So yes, this Physics Friday is shorter than some other ones, which is both a good thing and bad thing, I suppose. But at any rate, hope you all enjoyed, and I will see you all in the next one. Adios!